This first illustration models the mysterious cloud view of the internet. Casual users see information go into and come out of the internet, and they understand what kinds of information and services are available. Email services, web pages, online retailers, banking institutions, and more. But they may not understand how that information is networked together. Let's take a closer look at the structure of the internet so that the cloud is not so mysterious. This next illustration begins to show how the internet is networked together in a little more detail. It shows how the internet is arranged loosely into a hierarchy. At the top of the hierarchy is what is referred to as the backbone of the internet. The backbone of the internet consists of the largest set of internet service providers, or ISPs as they're called. An ISP is an organization that owns, controls, and maintains a large number of the computer networking cables and networking devices that make the internet possible. These largest ISPs include corporations, governments, and in some cases large academic organizations. The connections linking the biggest ISPs together are modeled by red arrows in this illustration. These arrows represent the network cables that carry the most information. Most internet traffic must travel through one of these backbone connections at some point as it travels across the net. As we work our way down the hierarchy, we see that there is a tier of medium-sized ISPs. These medium-sized ISPs are responsible for considerably less internet traffic and considerably fewer cables and networking devices than the backbone ISPs are. But they are still responsible for a huge amount of traffic. In this illustration, the blue arrows represent the internet traffic between these medium ISPs and the backbone ISPs above them. The green arrows represent the connection between the medium ISPs and an organization further down the hierarchy. As we can see in the illustration, a business with its own private internal network might connect its many users directly to one of these blue medium-sized ISPs. However, a residential user might connect to the medium ISPs through an even smaller local ISP. These small, local ISPs that connect residents to the internet are often controlled by a local cable company or a local phone company. The connection between the smallest tier of ISPs and an individual residence is represented here by a purple arrow. The connection represented by the purple arrow might carry a lot of information, streaming video, file downloads, or maybe online games. But that quantity of information is just nothing compared to the quantity represented by the arrows higher up on the hierarchy. So there it is. This illustration shows us how internet service providers are organized into a hierarchy, with the ISPs on the top handling the most data, and the ISPs and residents on the bottom handling the least data. This next illustration shows something else. As you may already know, every device that is connected to the internet has a unique address called an IP address. This illustration shows a couple different ways that IP addresses get assigned to devices. This diagram includes three fictional networks: the XYZ Office Network, the ABC Office Network, and the Joe's Coffee Shop Network. To keep the diagram relatively simple, the rest of the internet has been condensed down into a cloud in the middle of the illustration. First, let's take a look at the XYZ Office Network on the left side of the illustration. Those red numbers are the IP addresses for the whole network. Every IP address is numerical like that. They are always written as 4 sets of digits, each separated by a period. Each of these 4 sets of digits can be any number from 0 to 255. So take a look at the IP address of the XYZ network. It's 197.12.15.0. All of the devices connected to the XYZ network will be assigned IP addresses that begin with the first 3 sets of digits, 197.12.15. Device IP addresses ending in 0 are restricted, and device IP addresses ending in 255 are also reserved, so in practice, the range of possible IP addresses for devices on this network are 0.1 to 0.254. As we can see in the illustration, the router at the XYZ Office Network has been assigned the IP address ending in 0.254. Meanwhile, Carol's desktop computer has been assigned the IP address ending in 0.10. There are 252 IP addresses remaining in the available range for this network. The XYZ Office Network uses static IP address assignments. Static IP addresses are unchanging. That means that for the foreseeable future, Carol's desktop has been permanently assigned this particular IP address. 197.12.15.10 is permanently reserved for her computer. The opposite of static IP address assignment is dynamic IP address assignment. For an example of dynamic IP address assignment, let's take a look at the ABC office network over on the right side of the illustration. The ABC office network is at the IP address 207.10.2.0. Just like in the case of the XYZ office network, devices connecting to the network can use any IP address starting with those first three numbers and ending with any number from 1 to 254. For example, on this network, the router took the IP address ending in 254, Bob's computer took the address ending in 15, and Alice's computer took the address ending in 5. But unlike the XYZ network, the ABC office network uses dynamic IP addresses instead of static IP addresses. This means that some of these IP addresses are subject to change. You see, the ABC office network has a special piece of hardware called a Dynamic Host Configuration Protocol Server, or a DHCP server, as it's often abbreviated. The Dynamic Host Configuration Protocol Server assigns a device one of the 254 possible network IP addresses each time a device begins a new internet session. The DHCP server will lease each IP address for a set period of time, and after that time passes, then the device will have to renew its lease. I know that I'm throwing a lot of new information at you, but I promise that the underlying concept isn't very difficult. All we're saying is that, for example, Bob's computer has the IP address ending in 0.15 for now, but it might be assigned a new IP address once the hour is up. What are the advantages and disadvantages of dynamic IP addresses versus static IP addresses? Well, the advantage of a static IP address, like Carol has on her computer, is that her IP address is always available to her. She has a reserved place on the router. When IP addresses are assigned dynamically, as they are for Bob's computer over here, then there's a chance that there won't be any room for him when he tries to connect to the network. If the DHCP server has already assigned all the IP addresses available to it, then there won't be any left for Bob. The advantage of dynamic IP address assignment is that dynamic assignments are more flexible. Thousands of different devices could connect to the ABC network, and as long as they don't all try to connect at the same time, the DHCP server can assign them all an IP address on the network. Let's look down at the bottom of this illustration to see one more network configuration that also uses dynamic IP address assignments. Joe's Coffee Shop network is at IP address 207.10.3.0. This means that devices connected to it can take the IP addresses beginning with those three numbers and ending with a number between 1 and 254. Over the course of, say, a month, a coffee shop could probably expect to have many more than just 254 devices connect to their wireless connection. But at any given time throughout the day, they would probably have only a few devices connected, maybe 50 or so. This is a perfect situation for dynamic IP address assignments. The network only has 254 IP addresses that it can assign, but it can easily accommodate all of its users by assigning these addresses on a temporary basis only to the users who are active on the network. But remember, when we were examining the ABC office network connection, we saw that a network needs a dynamic host configuration protocol server in order to accommodate dynamic IP addressing. Where is the DHCP server at Joe's Coffee Shop? The answer is that at Joe's Coffee Shop, the DHCP server is combined with the internet router. Instead of the router and the DHCP server being two separate devices, they're integrated together into a single device. This is pretty common. Most home internet routers also have DHCP servers built into them, and so most home networks can accommodate dynamic IP address assignments. So, what are the big takeaways from this illustration? I want you to see that a computer's IP address usually depends on a router's IP address. I also want you to see that your device's IP address can change depending on what network it's on and depending on whether the network uses dynamic or static IP address assignment. Finally, I want you to note the structure of an IP address, that it's 4 numbers separated by periods. The last illustration that we will examine in this lecture models the difference between a public IP address and a private IP address. In our discussion of IP addresses so far, we have not been making the distinction between public and private IP addresses. I've been speaking as if all IP addresses are the same, but there is a significant difference between public IP addresses and private IP addresses. This illustration shows two different networks that are connected to the internet: Alice's home network and Bob's home network. Alice's home network is composed of two devices, a router and Alice's computer. Bob's home network is composed of four devices, a router, Bob's computer, Carol's computer, and a printer. Let's take a look at Bob's home network on the right side of this illustration. Bob's local internet service provider has only assigned him one IP address, but he would like to connect two computers to the internet, his and Carol's, and furthermore, he'd like to connect his wireless printer to his home network. The rules of IP require that every device has its own IP address, but Bob's internet service provider has only given him one IP address to work with. So what does Bob do? He will use his router to create a private home network to connect his four devices together. And then he'll connect his entire home network to the public internet through the IP address that his internet service provider has assigned him. From the perspective of somebody outside on the public internet, Bob appears to have only one device connected to the internet, and that's his router. But Bob's router can coordinate Bob's public internet connection with multiple devices on his private network. So from within the private network, we can see that there are really three more devices connected to the public internet through Bob's router. Now let's compare Bob's home network to Alice's home network on the bottom left portion of the illustration. Both networks have a public IP address, and those public IP addresses are unique. Indeed, every public IP address must be unique. However, Bob's and Alice's routers help them to create private networks, and these private networks can reuse the same IP addresses. For example, we can see that Alice's computer's private IP address is identical to Bob's computer's private IP address. This repetition is possible because of the distinction between their private IP addresses and their public IP addresses. It's kind of like how every apartment building in a city must have a unique street address for the post office to deliver mail to. But at each unique street address, the apartment buildings can reuse the same apartment numbers.